Okay, atomic mass. So one of the things that Dalton wasn't quite right about is he said that all atoms of a given element have the same mass, sometimes called the atomic weight. We now know that that's not exactly true. We don't have to throw out his whole theory, we just need to modify it a little bit. All atoms of the same element have the same number of protons. That's true. So different elements have different masses. Those are called isotopes. We can calculate an average mass. That's called the atomic mass for each element. Except in very limited situations, we're not dealing with 2 or 3 atoms where we would care about the mass of each individual one. We're usually dealing with bajillions of them. And so what we're more interested in is what's their average mass. So on the periodic table, here's one box from the periodic table. There's a number under the element symbol, and that number is not a nice whole number. That is the average mass of that particular kind of atom. So chlorine has an atomic mass of 35.45. That means that the average atom weighs 35.45 atomic mass units. We get those numbers by averaging all the different isotopes that are found for that element. Instead of what's called a simple average, where you take all the individual numbers, you add them up and divide by the number of numbers, here we're dealing with really, really large numbers of atoms. So we use a weighted average, and we find the percent abundance for each of the isotopes, and we do a weighted average.
So why do they do that? I was like going over the homework.
Mm-hmm.
Usually, like in math, when you take the mean average, you add them all up and divide
Right.
by however many of whatever you added up.
The problem with atoms is you might be adding up like 10 to the 23rd numbers, which is going to take you longer than your lifespan, right? And so instead of doing that, we can say, well, 50% of them have this weight, and 25% have this weight,
Now, is
and
that an
25.
average itself of that 50%?
No, the 50%, we would look at all the different atoms or isotopes for that element and say, okay, 50% of them have this mass, and 25% of them have this mass. And so then we know that we can multiply the 50% by 0.5.
I was just asking because so you multiply the percentage of how abundant it is times the mass, but is that mass of that 50%, is it an average of the 50%?
No. That one group of isotopes, that single kind of isotopes, all of those have exactly the same mass.
Right.
Yeah. Good questions. So let's look at an example for chlorine. So naturally occurring chlorine, 75.77% of it is chlorine-35 atoms. So those have a mass of 34.97 atomic mass units. The mass of that atom is going to be very close to the atomic mass of the isotope. I'm sorry, the mass number of the isotope. That's what I meant to say. The atomic mass of the isotope is very close, but slightly smaller than the mass number. So 75.77% of chlorine-35. 24.23% is chlorine-37. And so that mass is slightly smaller than the mass number. Yeah?
How does an atomic mass unit compare to like other units of mass? Is it?
Well, you can figure out what an atomic mass unit is in grams. I don't know that off the top of my head, except it's really, really, really small. We don't figure that out. I don't remember it because it's not very useful. So atomic mass unit is the unit that we use when we're talking about an individual atom, because grams are way too small. I mean, the grams are too big, and we end up with these crazy small numbers. Okay, so to calculate the atomic mass of chlorine, the average mass of chlorine atoms, we're going to take the percent abundance and make it into a decimal form. So we take the percentage, divide by 100. Okay? So 0.7577. And then we multiply by the mass of that isotope. And then for the other isotope, we take its percent abundance, turn it into a decimal form by dividing by 100, multiply by its mass. We take those and we add them together, and that gives us the average mass. Now, you could use the percentage. You could take the percentage times this and the percentage times that, add them together, but then you'd have to divide by 100. This is an average. It's just not a simple average. Remember that averages also always have to be between the highest number and the lowest number. If you get something that's outside of that, something went wrong. Question?
On the first online homework, when we did this, when you watch the video, at the very end, he's like, because there's 4 decimal spots, you round to the second decimal place. But what I wasn't understanding is the 26.4968 plus 8.9578. In terms of sig figs, I thought you would leave 4 decimal, like 4 spots after the decimal.
That's an excellent question. So what about sig figs here? So when we've got this one, 4 sig figs times 4 sig figs, so this number really has 4 significant figures.
Oh, okay.
So that would be the 9.
Yeah.
And the next one also would have 4 sig figs. And so that when you add those together, you're going to go with the fewest decimal places.
Got it.
Good question. So this is a general form of the equation for calculating atomic mass, which may or may not be any help at all to you. It's the sum of all the isotopes. You take the fraction of one isotope and you multiply it by the mass of that one isotope. You do that for each isotope and you add them together. So there could be 2 isotopes, there could be 5 isotopes. So let's do an example. Magnesium has 3 naturally occurring isotopes with masses of 23.99 atomic mass units, 24.99 AMU, and 25.98 AMU, and natural abundances of 78.99%, 10.00%, and 11.01% respectively. So respectively means that the order of the masses is the same as the order of the percentages. Calculate the atomic mass of magnesium. So this 78.99 goes with the 23.99. I'm going to take that percentage and express it in a decimal form, dividing by 100 essentially. 78.99 times the mass of that isotope. Plus the percent abundance of the other one expressed as a decimal, 0.1000, times the mass of that one, 24.99. And the third one, 11.01%, that becomes 0.1101 times the mass of that one. What you need to be careful of is sometimes you'll have a percent abundance that's less than 10%, and when you divide by 100, you just need to be careful that you don't accidentally change the number. So 0.799 times 23.99 plus 0.1000 times 24.99 plus 0.1101 times 25.98 equals. So my calculator gives me a big mess, 24.309099 atomic mass units. But that average cannot be more precise than the numbers that we used to calculate it. So in general, without going through all the multiplying, dividing with, and the adding with the sig figs, This one has 4 sig figs. This one has 4 sig figs. This ends in the second decimal place, and so we're going to end this atomic mass in the second decimal place, and that also has 4 sig figs. If these only had 2 significant figures, then we'd have to round this a little bit more. I am not going to try to trick you with sig figs on these sorts of calculations. Just try to be close. So 24.31 atomic mass units. That's the average mass of a magnesium atom. When we're doing things with real elements, you can double check your answer on the periodic table, find magnesium, and periodic table says 24.3051, and so that agrees. If you get something significantly different, check your math. Any questions? Are there any magnesium atoms that weigh 24.31 atomic mass units? No, there aren't any. It's the average, right? If you have 2 children and one's 8 years old and one's 10 years old, the average age is 9 years old, but nobody's 9, right? Some of you might wonder, well, how do they figure out what the masses of these isotopes are? We use mass spectrometry, and this is the sort of result that you might get. This is for chlorine, and you'll get 2 bars here, one for the chlorine 35 isotope with a mass of 35, and one for this at 37. The scale here would be more detailed, but this just gives us the general idea. This is how the instrument works. So this is an evacuated chamber, because we don't want these particles running into gas molecules and doing stuff we don't want them to do. So you stick your sample in through this end. There's a heater that vaporizes it. So no matter what state it's in, it becomes a gas. It goes through some ionizing electron beams and then gets a negative charge. Because it has a charge, now we can accelerate it using electric fields, and we can focus it, and so we're sending a beam of these charged particles through this magnetic field, and these are very powerful magnets. The magnetic field is going to separate the particles based on their mass to charge ratio. So they will have picked up at least 1 electron. Some of them might pick up 2 or more. You can't really control that. As they come through here, the magnetic field is going to bend this beam of particles. And it's going to bend the lighter particles farther or more than the heavy particles. And so they're going to get separated based on their mass to charge ratio.
Because their momentum is...
Yeah, the heavy particles have more momentum, and so it takes more to change their direction. The lighter particles have less momentum, and so they're more easily changed, and so we can separate them based on their masses. That's the general idea. Of course, the actual details are a little more complicated than that. Any questions? Not going to test you on the details of a mass spec.